Hello and welcome. In this video we want to take a look at Stokes' theorem, and Stokes' theorem is an extension of Green's theorem to parametric surfaces. Now let's remember what Green's theorem is. So if you're given a vector field vector field in R2, and we're calling it f of xy equals p comma q, where p and q are both functions of x and y, and you've got C, a simple closed curve bounding a region D, and oriented counterclockwise, right? So you're going, around the region counterclockwise. Then the line integral around the curve C of f dotted with dr is the double integral of partial of q with respect to x minus partial of p with respect to y dA, and that's the double integral over the region D. Okay. Now, there's nothing in here that at the time we never mentioned curl. We're in the plane, and there isn't a strong notion of curl in the plane. It's really a 3D thing. But if we think of this vector field PQ in the following way, we think of it as a vector field in R3. So f of xyz is p of xy comma q of xy comma 0. Notice nothing's a function of z here, but we're still embedding it into R3. So once you get this into R3, you can calculate the curl, and you can follow the curl formulas. The fact that this one's an R, and the fact that these are not partials with respect, each time you need to take the partial with respect to z, you're going to get a 0 out of that. And on this one, you're going to get zeros for all the partials because it is 0. So there's a lot of zeros that happen here. And the only thing that's non-zero is this third term, which ends up being the partial of q with respect to x minus the partial of p with respect to y. And that's precisely what you're integrating here. So Green's theorem now looks like, sorry, recording this rather late at night, and my ability to edit things, see mistakes before I get to the point of recording is minimal. So anyway, things keep appearing as I fix them on the fly here. So anyway, Green's theorem looks like this. The line integral around C of f dotted with dr is double integral over D of the curl of that vector field dotted with k dA. And notice the k here is 0, 0, 1. It's 1 up in the z direction. And since this vector field is completely in the xy plane, it makes sense that the curl should be perpendicular to, any flow that's happening. Any flow that's happening is happening in the xy plane. And so the curl would be a vector pointing upward in the z direction. And it's also a unit normal vector. So this is precisely, this NdA is precisely what we were doing for a flux integral, right? Anyway, the curl dotted with the normal vector there gives us what we're integrating here for Green's theorem. So let's see how that turns into Stokes' theorem. So here we go. Let S be a piecewise smooth oriented surface with a boundary that is a simple closed curve C with positive orientation. So if this is your surface, then the boundary is going around it. We have an orientation. This is drawn with the orientation pointing upwards, and so that would mean counterclockwise would be the positive orientation for C. If the n was pointing downward, then you'd go the other way. Right? You want to match the boundary orientation with the orientation of the surface. So you got all that. Then you got a vector field F with component functions that have continuous partial derivatives on an open region containing the surface. Then the line integral around the boundary of the vector function is the surface integral of the curl dotted with ds. So the only difference here is that Green's theorem does this flat on the xy plane, Now Stokes' theorem says let that region not just be a flat region in the plane, but let it be a curved surface potentially. And if you're integrating the vector field around the boundary, that's the same as doing the double integral of the curl um, over the whole surface. Okay. And the proof, I always like it when books do this, the proof is beyond the scope of this book. You'll have to look it up in some more advanced text. But here's here's a rough idea of what's going on. And honestly, I'm grabbing this picture straight out of the book, so I didn't create this myself. This is what are we using? OpenStax, Volume 3 for calculus. What they do is they say, well, let's take that surface and cut it up into a bunch of really small pieces, and we can assume that each of those pieces is a flat rectangle. Actually, I think they say square, but whatever, it could be rectangles or squares. And then they say, okay, we are going to do, if you look at the surface integral, right, of the surface integral of the curl, ds, Green's theorem allows you to say that on those little flat patches, that integral of the curl is equal to the line integral around the boundary of each little rectangle or each little square. And then you say, well, if you add those up over the whole surface, which is what the double integral would be doing, then you're doing things like this, where you got side-by-side little squares where the line integral going around uses this edge going one way for this piece, and it uses it going the other way for this other piece, and so that cancels out. And in fact, any of the edges that are interior here get completely canceled out. So all of these little line integrals around each one of those little squares is canceling each other out, except for when you get out towards the edge, and the one out here would not be. Right? That would not be. It's not canceled out with anything right there. And what you end up with is you end up with the only stuff that doesn't cancel out is the line integral around the outside. Okay, and that's the gist of the proof. It's not all the details. Okay, but this really makes a lot of sense to me in that, we think about the curl as the spin, and you think at each point, how's that spin happening? And the next point, how's that spin happening? Well, if you got 2 points side by side, you're going to have one spin going this way and one spin going that way. Those are canceling out. And really all you're going to see is it all propagates out to the edge, and you just see that spin happening on the boundary. So you just integrate around the boundary to see what's going on. And that's Stokes' theorem. Okay. Green's theorem as well, but Stokes' theorem when you bend it onto a curved surface. Okay. Now, we do have a rigorous proof in a special case that the book goes through it, but I'm going to do it right here because there's a bunch of stuff that goes on, and oh my goodness, it gets pretty complicated pretty fast. But you can read it if you don't want to listen to me. But then again, you might want to listen to me because I'm going to explain some of the steps that all of a sudden go kind of crazy. So here we go. This is going to be the case where the surface that I'm integrating over is or can be described as z is a function of x and y. Okay? So not typically the way we think of parametrized surface, but just a surface, z is a function of 2 variables. Okay, so suppose you got S that way, defined as z is a function of x and y, over some bounded simply connected region D in the xy plane. The word bounded I don't think we've used before. Bounded just means that it can be contained within a disk, so it's finite area, but more than finite area, it's actually finite in any extent that it doesn't head off to infinity in any direction. The book just says it needs to be a finite, just have finite area, but that's not true because you can have things with finite area that have these infinitely long tails, and I don't want that. I want a finite length region. Okay, so anyway, it's bounded. That's what that means. Bounded, simply connected region D in the xy plane. And assume that this function f has continuous second partial derivatives. Let C be the boundary of the surface S, and let C prime be the boundary of D. Now, I debated here a little bit. The book uses C prime. Prime notation generally means derivative, but it doesn't here. It's just other. Just C was already used for the boundary of S, and this is the boundary of D. Some textbooks actually use the partial symbol, like a partial derivative, to talk about boundary. So instead of calling the boundary of SC, they would call the boundary of S partial S. And likewise, they'd call the boundary of D partial D. And I thought about using that, and it's like, I'll just talk about it. Either way, it looks like I'm taking a derivative, but I'm not. Okay, this is just a label here for the boundary of D. And so all positive orientations. So you got the surface was have to have an orientation on it, and then the boundary has to be oriented positively with respect to that, all that kind of stuff. Now we got a vector field F, which is P, Q, R. Notice that this is a vector field in R3, so it's a function of X, Y, and Z. So P is a function of X, Y, and Z. Q is a function of X, Y, and Z. R is a function of X, Y, and Z. Okay, and assume that P, Q, and R all have continuous partial derivatives. Now, here's my parameterization for the surface. I'm using capital R here just because I'm going to use little r when I talk about parameterizing the boundaries. So anyway, the surface is parameterized by capital R, x comma y comma f of x, y. So instead of u and v, I'm actually using x and y as my parameters here. This is pretty much standard way to parameterize a surface that's already known as z as a function of x and y. So rather than the partial of r with respect to u and v, I'm going to take the partial of r with respect to x and y. So this is partial with respect to x is 1, 0, and then the partial of f with respect to x. And with respect to y, it's 0, right? 0, 1, and the partial of f with respect to y. I take the cross product here to get the normal vector. That will be my orientation for S. So you take this cross product. There's minus f sub x. There's minus f sub y, and then 1 right there. And I notice that this is the upward normal, the way I've done this, and I know it's upward because the z component is positive, right? So wherever that surface is, the normal vector here is pointing upwards. Okay, so I want to prove that Stokes' theorem, right? I want to prove that the line integral around here is equal to the double integral of the curl over the surface. So I'm going to essentially do both of these and see that I get the same thing. Okay. So let's start with the double integral, the surface integral. So the surface integral of the curl dotted with the capital vector S, right? This is a little bit of surface area. We saw in previous videos that that's equal to, here's the curl vector, right? The curl vector field dotted with, so this is the normal vector times dA. Now taking that dot product, I get this, so just first component here times first component, second component, third component, add them up, right? So there's that. In this next step, I'm doing, actually, I think all I did was I changed the f sub x to z sub x and f sub y to z sub y. I mean, z is f of xy, so f and z are somewhat interchangeable. So I've just switched the f's into z's. They're interchangeable. It's a matter, do you want to think of it as a variable z, or do you want to think of it as a function f? And we need to do both. So we need to realize that although there is a variable, we're in R3, so there's a variable z, but in the parameterization to stay on the surface, z is a function of x and y. So that's the f. Okay. Now I'm going to use lowercase r of t to parameterize the curve C prime. So this is the boundary of D down in the xy plane. And then I'm using the same R. I don't think it makes too much difference here. But here's another parameterized curve, x of t, comma y of t, comma f of x of t, comma y of t. So this is just a parameterization of the boundary of the surface, right? So this is, you know, in 2D, so this one right here, this is just the boundary in the xy plane, and then this one here is you move it up onto the surface, and it's the boundary on the surface. So now let's look at the line integral around C of f dotted with dr. That's this r. Right? And we can write that as the line integral of p dx plus q dy plus r dz. This is going way back to our definition of line integral of a vector field along a curve. Okay. Now the dx is, looking here, it's going to be x prime, y prime, z prime, right, dt. So that's what we have there. But z prime now, z prime is the partial of z with respect to t, but z is both a function of x and y. So z is a function of x and y are functions of t. So the derivative of z with respect to t has two parts. It's the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. So that's a chain rule from Calc 3. Right? We're going to see chain rules a couple of times here. Okay, so now I'm going to essentially just distribute this r through here and then recombine things. The two things that have x primes get together and the two things that have y primes get together. So there's a p and an r times f sub x, that's times x prime, and there's a q and an r times f sub y times y prime. Now, and that's all, of course, integrated dt. Oh, at some point when I switch to t's, I just put in the a and b. That's to get me going all the way around the curve, right? But now, this right here is just in the xy plane. There's no z primes anymore. I got rid of the z prime by turning it into x primes and y primes. So this is just the definition of the line integral around c prime of this dx plus that dy, right? That the x prime dx is, sorry, the x prime dt is the dx, the y prime dt is the dy. And now I can use Green's theorem in the plane to say that this line integral around c prime is the double integral over d of this partial of this one with respect to x minus the partial of this first one with respect to y. Okay. Now, I'm going to take some partial derivatives here, and we've got to be real careful. At this point, I want to do this. So remember, q is a function of x, y, and z. But z is a function of x and y, and so are, so x and y are functions of x and y. Okay, well. So when I'm going to take the partial of q with respect to x, there's two ways to get there. I can go this way, or I can go this way. Likewise, when I take with respect to y. Similar things are going to happen with r and with p and r, whatever order they're in. That q is a function of three variables, but one of those variables is a function of the other two. Okay, so let's go back here. So here we go. Partial of this right here with respect to x. So the partial of q with respect to x is the partial of q with respect to x plus the partial of q with respect to z times the partial of z with respect to x. Right? And this is when you're reading the textbook, it's like, you just, I'm just going to take the derivative, this, okay, I'm going to get two things. This is a product rule, I'm going to get three things, because this will give me one and this will give me two. But yet, I get five things out of this. It's like, what? How'd that all happen? So, the thing is, this one right here, partial of q with respect to x, has two pieces to it. Likewise now, there's a product rule. Partial of this product with respect to x is I'm going to take the partial with respect to r times this thing, and then the partial of this thing times r. So the partial of r with respect to x, again, I've got that problem that r is a function of x, y, and z is a function of x and y. So the partial of r with respect to x is the partial of r with respect to x, plus the partial of r with respect to z times the partial of z with respect to x. And these partial of z's with respect to x, you could write them as partial of f with respect to x if you wanted to, because z is f of x and y. Right? So that's that. So that was the partial of z with respect to r. Now I need to multiply that times z. So that's partial of r with respect to x now times z with respect to y. And then I need r times the partial of this thing with respect to x, so that would be z, y, x. Right? So that's actually the mixed partial now. So there's that. Minus partial of all this stuff with respect to y. And again, this is going to have some pieces to it because p and r are both functions of x, y, and z is a function of x and y. There's a lot of chain rules involved here. So the partial of p with respect to y is the partial of p with respect to y plus the partial of p with respect to z times the partial of z with respect to y. Right? There's those two paths to get down there. And then I need the partial of this thing with this product with respect to y. So the partial r has got two pieces times the partial z with respect to x plus then r times this, right? So and this partial of r with respect to y is the partial r with respect to y plus the partial r with respect to z times the partial z with respect to y. Chain rule, right? There's like 1, 2, 3, 4 chain rules in here that are coming through. Okay. And notice that this one right here, when I did this term, it was just r times. I had the partial of z with respect to y, and I was taking that with respect to x. This last one here, I'm going to have r times. I've got the partial of z with respect to x, and now I'm taking with respect to y. Right, so there's that right there. Now, and this is dA. So the dA is just barely off the screen. Now, I'm going to distribute a whole bunch of stuff through. Am I rearranging things yet? Yes, I am. So I'm distributing this z sub y into there. I'm distributing the minus sign into this and that into there. And I'm collecting things that have z sub x in it. So this term right here is right there. And the minus r sub y zx is that one right there. I don't know if you can see me pointing. So the first term is here. The second thing here came from the minus z r, so the minus ry zx, that's this one, and the rx zy is rx zy, and the minus pz zy is the minus pz zy right there. The qx is that first one right here. The minus py is that thing right there. And then there's a bunch of other stuff that's also in there. So there's this r z z x z y, and this r z x y, and there's these two that are on the end with minus signs in front of them. Okay, and I want to point out that this term and that term are the same except with the opposite sign in front of them. And this term are the same because Clairaut's theorem says that f sub xy is the same as f sub yx, right? That the mixed partials are equal if they're continuous, and we assume that we had second partials continuous. So those four terms disappear, and what I get is this, which, if you scroll back up above, that's what I got with the double integral. Is it the same? So this is qz minus ry. This is qz minus ry. Yep. Anyway, they're the same. So Stokes' theorem is true for this case. I mean, I don't see that there's any intuition gained from this proof, right? The intuition, I think, comes from that first one we did, where you break it up into little pieces and you look at this, the circulation integral, and relating it to, with Green's theorem, you're relating it to the double integral of the curl, and that all the stuff inside just cancels out until you get to just what's happening around the edge. All right, I did want to go through this again because it's really bonkers in the book to see where this thing turns into this, where this thing turns into this. It's just, how's that happen? Chain rule. All right, well, we're gonna have to do some examples, but we'll do that in the next video.